Tonight, we're going to confront one of the strangest facts in all of physics. Empty space, genuine vacuum, with nothing in it, can suddenly produce real, detectable particles. Not as a metaphor, not as a thought experiment, as a measured physical process. If you take two metal plates and place them close enough together in a vacuum, a force appears between them, a force created by the activity of fields in what should be pure emptiness. If you place an intense enough electric field across empty space, that space will spark, producing electrons and their antimatter counterparts from apparently nothing at all. And near a black hole, the vacuum itself radiates particles into the cosmos as though space were glowing. This sounds like it violates everything we know about energy and matter, but it doesn't. And the reason why reveals something extraordinary about what empty space actually is. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Think about what it means for something to be truly empty. Not just a room with the furniture removed, not just a box with the air pumped out. Truly empty. No atoms, no light, no radiation, no particles of any kind. Nothing. Just space itself, extending in every direction with absolutely nothing inside it. This is what most people picture when they hear the word vacuum. An absence, a void, the purest form of nothing that could possibly exist. And for most of human history, that understanding seemed perfectly reasonable. If you remove everything from a region of space, what's left? Nothing. That's the obvious answer. It's the intuitive answer. It's also, as it turns out, completely wrong. The vacuum of modern physics is not nothing. It is not empty in any meaningful sense. It is not a blank stage waiting for matter and energy to show up and perform. The vacuum is a physical state, a real, measurable condition of underlying fields that fill every point in the universe. Understanding this single idea changes everything about how particle creation works. Because once you realize that so-called empty space is actually a field state with genuine physical properties, the fact that it can produce particles stops sounding like magic and starts sounding like physics. But to appreciate why this matters, you need to understand how our picture of empty space evolved. Because it took centuries of hard-won physics to arrive at the modern view. And the journey reveals just how deeply our everyday intuitions can mislead us about the nature of reality. For most of recorded history, people assumed that the universe was fundamentally made of stuff, objects, things you could pick up or point to, rocks, water, air, fire. The ancient Greek atomists, most famously Democritus around 400 BC, proposed that everything was built from tiny, indivisible particles moving through void, through genuinely empty space. In their picture, you had matter on one hand and nothing on the other, and there wasn't anything in between. The void was simply the absence of atoms. It was the gap between things. It had no properties of its own. It didn't do anything. It was just there, passively allowing atoms to move through it. This was a remarkably modern idea in many ways. But notice what it assumed about empty space. The void was truly empty. It was nothing. It contributed nothing to the physics of the universe. Not everyone agreed. Aristotle rejected the very idea of a void. He argued that nature does not permit emptiness, that every region of space must be filled with something. If you remove the air from a container, something else rushes in to fill it. A true void, for Aristotle, was logically impossible. This wasn't just philosophy, it was a physical claim, and it dominated Western thinking for nearly 2,000 years. For most of that time, no one could test it, because no one could create a vacuum in a laboratory. There was no way to pump the air out of a sealed container. You could argue about whether a void was possible, but you couldn't check. That changed in 1643, when the Italian physicist Evangelista Torricelli performed a beautifully simple experiment. He filled a long glass tube with mercury, sealed one end, and inverted it into a dish of mercury. The mercury in the tube dropped part way, leaving a gap at the sealed top. Below was a column of mercury. Above was a space with no air, no mercury, apparently nothing at all. Torricelli had created the first laboratory vacuum, or at least the first convincing approximation of one. The result was electrifying. Aristotle's supporters were horrified. If nature abhors a vacuum, how could one be sitting right there in a glass tube on a laboratory bench? Torricelli argued that the mercury was held up not by nature's horror of emptiness, but by the weight of the atmosphere pressing down on the mercury in the dish. The space above the mercury really was empty. It contained nothing but the faint vapor of mercury itself. A few years later, in 1654, the German physicist Otto von Guericke staged one of the most dramatic demonstrations in the history of science. He took two large copper hemispheres, placed them together to form a hollow sphere, and pumped the air out using a vacuum pump he had invented. Then he attached teams of horses to each hemisphere and had them pull in opposite directions. The horses could not pull the hemispheres apart. The pressure of the outside atmosphere, pushing against the vacuum inside, held them together with enormous force. Von Guericke's Magdeburg hemispheres, named after his city, proved that the vacuum was real and that it had measurable physical consequences. Even in the 1600s, the vacuum was already demonstrating that emptiness is not as simple as it sounds. Removing the air created not passive nothingness, but a physical condition with real effects. Still, the prevailing view for centuries afterward remained straightforward. A vacuum was simply the absence of matter. Whatever strange pressure effects it produced were caused by the surrounding atmosphere, not by properties of the empty space itself. When Isaac Newton developed his laws of motion and gravity in the late 1600s, he described the universe in terms of particles moving through absolute space. Space, for Newton, was a fixed, unchanging stage. It had no physical properties. It didn't interact with matter. It was simply the container in which everything happened. You could, in principle, remove every particle from a region of space, and what would remain would be genuinely empty. A perfect void with no physical content whatsoever. This picture of absolute empty space formed the foundation of physics for over 2 centuries. Generations of scientists were trained to think of space as a passive backdrop, an inert stage on which the real drama of physics played out. And for everyday physics, this works perfectly well. You don't need to worry about the quantum properties of empty space when you're calculating the trajectory of a cannonball or the orbit of a moon. Newtonian physics treats space as a passive container, and that approximation is excellent for the kinds of problems Newton cared about. If you're building bridges or launching rockets, empty space really is just empty space for all practical purposes. But there were already hints, even in the 1800s, that something deeper was going on beneath this tidy picture. Physicists studying electricity and magnetism began to realize that forces between charged objects couldn't be explained by particles alone. When you hold 2 magnets near each other, you feel a force between them. But how does one magnet know the other is there? The magnets aren't touching. There's a gap between them, apparently filled with nothing. And yet, something crosses that gap to create the force. How does the force get transmitted across apparently empty space? Michael Faraday, working in the 1830s and 1840s, proposed a radical idea. He suggested that electric and magnetic forces aren't transmitted directly between objects. Instead, he imagined that charged objects create invisible fields that spread out through space in every direction, and other charged objects respond to those fields. The field exists everywhere between the magnets, around them, far away from them. It has a value at every point, a direction, and a strength. And it's the field, not the objects themselves, that carries the force. This was a profound conceptual shift. Faraday was saying that the space between objects isn't truly empty. It contains something real, a physical entity with measurable properties. You can't see it or touch it, but it's there, and it has effects. The field fills the gap between the magnets. It fills all the space around every charged particle in the universe. It permeates regions that look completely empty to the naked eye. James Clerk Maxwell formalized Faraday's intuition into rigorous mathematics in the 1860s, producing his famous equations of electromagnetism. Maxwell showed that electric and magnetic fields aren't just useful fictions or convenient ways of visualizing forces. They're physically real. They carry energy. They carry momentum. And most remarkably, they can propagate through space as waves, traveling at a specific, calculable speed. When Maxwell calculated that speed, it turned out to be the speed of light. This meant that light itself, visible light, radio waves, X-rays, gamma rays, all of it, is nothing more than electromagnetic field disturbances rippling through space. This was an extraordinary realization. Light is not a substance traveling through a void, it's a disturbance in a field, a wave pattern in something that fills all of space. But this immediately raised a question that consumed physicists for decades. If light is a wave, what is it a wave in? Water waves need water. Sound waves need air. Surely light waves need some medium to ripple through. The idea that a wave could propagate through literal nothingness seemed absurd to 19th century physicists. They needed something to fill the void. So they invented one. They called it the luminiferous ether, a hypothetical substance filling all of space, invisible, weightless, perfectly transparent, yet rigid enough to transmit light waves at enormous speeds. The ether was supposed to be the medium through which electromagnetic waves travelled, the fabric of empty space itself. It was an elegant idea. It preserved the intuition that waves need a medium, and it meant that space wasn't truly empty after all. It was filled with this invisible substance. But the ether had a problem. If it existed, it should be detectable. Specifically, as the Earth orbits the Sun, it should be moving through the ether at different speeds and in different directions at different times of year. This motion through the ether should produce measurable effects on the speed of light. Light travelling in the same direction as Earth's motion through the ether should appear slightly slower, while light travelling against the motion should appear slightly faster, the same way sound travels faster downwind than upwind. In 1887, Albert Michelson and Edward Morley performed one of the most important experiments in the history of physics, designed to detect exactly this effect. They built an incredibly precise instrument called an interferometer that could measure tiny differences in the speed of light in two perpendicular directions. If the ether existed, and if the Earth was moving through it, the experiment would detect a difference. It found nothing. No difference at all. The speed of light was the same in every direction, regardless of Earth's motion. The experiment was repeated with greater and greater precision over the following years. The result was always the same. No ether wind. No detectable medium filling space. The luminiferous ether, the invisible substance that was supposed to fill the void and carry light waves, simply did not exist. This result stunned the physics community. It meant that light could propagate through genuinely empty space without any medium. It meant the void was truly empty. Or so it seemed. Einstein used this result as one of the foundations for his special theory of relativity in 1905, which showed that the speed of light is constant for all observers and that no ether is needed. Space, it appeared, was once again empty. But the triumph of emptiness was short-lived, because even as the ether was being demolished, the quantum revolution was beginning, and it would eventually reveal that space is filled with something after all. Not the rigid mechanical ether of the 19th century, something far stranger. Quantum fields. The ether was wrong, but the intuition that empty space contains physical reality turned out to be right, just not in any way the 19th century physicists could have imagined. The full revolution came in the 20th century, and it came from two directions at once. Both directions would converge on the same stunning conclusion. Empty space is not empty. The first direction was quantum mechanics. In the early 1900s, physicists discovered that energy comes in discrete packets called quanta. Max Planck showed in 1900 that electromagnetic radiation is emitted and absorbed in quantized units. Albert Einstein showed in 1905 that light itself comes in discrete packets, which we now call photons. Each photon carries a specific amount of energy proportional to the light's frequency. This meant the electromagnetic field isn't smooth and continuous at the microscopic level. It's granular. Its energy is bundled into chunks, indivisible units that cannot be broken apart. Then came Werner Heisenberg's uncertainty principle, formulated in 1927. This principle states that certain pairs of physical properties cannot both be known with perfect precision at the same time. The most famous example involves position and momentum. The more precisely you know where a particle is, the less precisely you can know how fast it's moving, and vice versa. This isn't a limitation of our measuring equipment, it's a fundamental feature of nature itself. The properties genuinely don't have precise, simultaneous values. But the uncertainty principle doesn't apply only to particles. It applies to fields as well. And this is where things become critical for understanding the vacuum. A field has a value at every point in space. Think of a calm lake. The surface of the lake has a height at every point. If the lake is perfectly still, the height is the same everywhere, and the rate at which the surface is changing is exactly zero. That's like a field in its lowest energy state in classical physics. A perfectly calm, perfectly motionless configuration. In classical physics, there's nothing preventing a field from being exactly zero everywhere, with exactly zero rate of change. That would be the classical vacuum, a state where the field is doing absolutely nothing. But quantum mechanics forbids this. The uncertainty principle, applied to fields, means that a field's value and its rate of change cannot both be exactly zero at the same time. These two quantities are related the same way position and momentum are related for a particle. If the field value were precisely zero at every point, its rate of change would be completely uncertain, which means it could be changing rapidly. And if the rate of change were precisely zero, meaning the field is perfectly still, the field value itself would be completely uncertain, possibly far from zero. This is not a measurement problem. It's not about our instruments being imprecise. It's not something we could fix with better technology. This is a fundamental feature of quantum physics, built into the mathematical structure of the theory. The field cannot be perfectly still. Even in its lowest possible energy state, even in what we call the vacuum, the field must jitter. It must fluctuate. There is a minimum amount of activity that quantum mechanics demands, and that minimum activity is always present, everywhere, at all times. You cannot remove it. You cannot reduce it further. It's irreducible. It's the quantum floor beneath which nature simply cannot go. The second direction of revolution came from quantum field theory, the framework that emerged in the late 1920s and 1930s when physicists combined quantum mechanics with Einstein's special relativity. This is where the modern understanding of particles and empty space truly takes shape, and it overturns something most people take completely for granted about what the universe is made of. In everyday language, we talk about particles as though they're the fundamental building blocks of reality. Electrons, photons, quarks. These are the things the universe is made of, right? That's how most people think about it. You start with particles and you build up from there. Atoms are made of particles. Molecules are made of atoms. Matter is made of molecules. The fundamental level is the particles themselves. But quantum field theory says otherwise. In quantum field theory, particles are not the fundamental entities. Fields are. The universe is filled with fields, one for every type of particle that exists. There is an electron field extending through all of space. There is a photon field, also called the electromagnetic field, extending through all of space. There is a quark field, a neutrino field, a muon field, a Higgs field, and several others. Each of these fields exists everywhere, at every point in the universe, right now as you listen to this. They are always present. They never turn off. They never go away. They pervade all of space continuously and permanently. A particle in this framework is not a tiny ball sitting in space. It's an excitation of a field. Think about what that means. When the electron field is in its lowest energy state, its ground state, there are no electrons present. The field is there, stretching across the universe, but it's as calm as quantum mechanics allows. Now, when energy is added to the electron field in the right way, a localized ripple forms. That ripple is what we detect as an electron. The electron is the ripple. Not a separate object that was placed on top of empty space, but a specific pattern of excitation in the underlying electron field. Remove the energy, the ripple subsides, and the electron ceases to exist. The field remains. Think about waves on the ocean. The ocean is always there. When it's calm, there are no visible waves, but the water hasn't vanished. The ocean is still present, still real, still filling the basin. When wind adds energy, waves form. Those waves travel across the surface. You can count them, measure their height, track their speed. They behave like distinct objects, but fundamentally, they're just patterns in the water. The waves aren't separate objects added to the ocean. They are the ocean, just in an excited state. Take the energy away, the waves die down, and you're left with calm water again. The waves are gone, but the ocean remains. Particles work the same way. An electron is a pattern in the electron field. A photon is a pattern in the electromagnetic field. A quark is a pattern in the quark field. Every particle you've ever heard of is a localized excitation in some underlying quantum field. Remove all the excitations, remove every single particle from a region of space, and the fields are still there. They don't vanish when you remove the particles, just as the ocean doesn't vanish when the waves stop. The fields persist, filling all of space, existing in their lowest energy configurations. This is what the vacuum actually is. It's not the absence of fields. It's the state where all the quantum fields are in their lowest possible energy configurations simultaneously. Every field exists everywhere, but none of them are excited enough to produce detectable particles. The vacuum is not empty. It is full of fields in their ground state. The difference between what we call empty space and what we call matter-filled space is simply the difference between calm fields and excited fields. The fields themselves are always there. And here's the key point that makes particle creation possible. Because of the uncertainty principle, those ground state fields cannot be perfectly still. They jitter, they fluctuate. Not wildly, not in ways that produce lasting, observable particles under normal conditions, but they fluctuate enough that the vacuum has real, measurable physical properties. The vacuum has energy. It exerts forces. It responds to external conditions. It is a physical state, as real and concrete as any other state of the quantum fields. This is worth pausing to appreciate because the implications are staggering. Every point in the universe, right now, contains all of the quantum fields known to physics. The space inside your room, the space between you and the walls, the space between atoms in your body, the vast emptiness between stars. All of it is filled with quantum fields. When those fields are in their ground state, you perceive that space as empty. There are no detectable particles, no light, no matter, no radiation. It looks and feels like nothing is there. But something is there. The fields are there. And they're not idle. They're fluctuating at every point, constantly, as a fundamental consequence of quantum mechanics. Paul Dirac was one of the first physicists to fully appreciate the implications of this picture. In the late 1920s, Dirac developed a quantum theory of the electron that incorporated special relativity, combining two of the great revolutions in physics into a single mathematical framework. His equation, published in 1928, was elegant and powerful, but it made a startling prediction that Dirac himself found deeply unsettling. The mathematics required the existence of a particle identical to the electron in every way, but with opposite electric charge. Nothing like this had ever been observed. Dirac initially struggled with what his equation was telling him. In his picture of the vacuum, what looks like empty space is really a state in which all negative energy electron states are fully occupied. A filled sea of electrons in negative energy states, invisible because there's nothing to contrast them against. Because every state is occupied and nothing stands out. If you add enough energy to knock one of these negative energy electrons out of the sea, you create a hole. That hole behaves exactly like a positively charged electron, an anti-electron. This particle, which Dirac's theory demanded, was eventually named the positron. And in 1932, the American physicist Carl Anderson detected it experimentally, confirming Dirac's prediction in spectacular fashion. This was extraordinary for a reason that goes beyond just discovering a new particle. The vacuum itself, through its mathematical structure, had predicted the existence of something no one had ever seen before. The properties of empty space, described by quantum theory, contained information about particles that could potentially exist. And when experimenters went looking with the right equipment and the right conditions, they found exactly what the theory predicted. The vacuum was not inert. It carried within it the blueprint for matter and antimatter alike. Now, the specific picture of a filled sea of negative energy electrons has been refined since Dirac's time. Modern quantum field theory doesn't describe the vacuum exactly that way. Instead, it treats the vacuum as the ground state of all quantum fields, as we've been discussing. But Dirac's core insight remains as profound as ever. The vacuum has structure. It has physical content. It contains information about all the particles that could potentially exist. And under the right physical conditions, those potential particles can become real. Let me be precise about what the ground state means, because this concept is central to everything that comes next. In quantum mechanics, every system has energy levels. An atom, for instance, has a lowest energy level called the ground state, and higher energy levels called excited states. When an atom absorbs energy, it jumps to a higher level. When it releases energy, it drops back down. An atom in its ground state is as calm as it can possibly be. But here's the crucial detail. Even in the ground state, the atom still has energy. A minimum, irreducible amount of energy that cannot be removed by any process. This is called zero-point energy. The energy a quantum system possesses even at absolute zero temperature, when every last bit of removable energy has been extracted. The same principle applies to quantum fields. Each field has a ground state, a lowest energy configuration. In that ground state, no particles are present, but the field has zero-point energy. It jitters around its average value, fluctuating continuously, restlessly, in accordance with the uncertainty principle. You cannot extract this zero-point energy by any ordinary means. It's the irreducible minimum. It's built into the very structure of the field by the laws of quantum mechanics. You can't calm the field further. You can't make it more still. The ground state is as quiet as nature allows, and nature insists on a certain level of noise. Now multiply this by the number of quantum fields that exist. The standard model of particle physics, our best current theory of fundamental particles and forces, describes roughly 17 distinct quantum fields, depending on how you group them. Each field has its own ground state. Each field has its own zero-point energy. Each field fluctuates independently at every point in space. The vacuum of the universe is the simultaneous ground state of all these fields at once. Every single one of them fluctuating at every single point in space, all at the same time. The vacuum is not one quiet field. It's 17 quiet fields, layered on top of each other, all jittering, all restless, all contributing their own zero-point energy to the background state of the universe. This sounds chaotic, and in a sense it is. But it's a highly structured kind of chaos. The fluctuations aren't random noise. They follow specific quantum mechanical rules. They have statistical properties that can be calculated with extraordinary precision. And they produce effects that can be measured in laboratories right here on Earth. Effects we'll explore in detail shortly. The zero-point energy of the vacuum is real. It's not an accounting trick. It's not a mathematical artifact that cancels out when you do the final calculation. It has genuine physical consequences that have been measured and confirmed. When physicists calculate the total zero-point energy of all the quantum fields in the standard model, they get a number. That number turns out to be extremely large. Embarrassingly large, in fact, because it doesn't match what we observe when we look at the large-scale behavior of the universe. This spectacular mismatch is one of the greatest unsolved problems in all of physics, and we'll return to it later. But the point for now is that the vacuum's energy is a calculable physical quantity derived from well-tested principles. It's as real as the energy stored in a battery, or the energy carried by sunlight. There's a useful analogy that captures some of this, though, like all analogies, it has limits. Imagine a vast field of grass on a perfectly calm day, no wind at all. Every blade of grass stands straight up, motionless. From a distance, the field looks perfectly still. This is like the classical vacuum, a field at rest, doing absolutely nothing. Now imagine zooming in with a powerful microscope. At the molecular level, those blades of grass aren't perfectly still. Thermal vibrations make them jitter slightly, even on the calmest day. And even if you could cool the grass down to incredibly low temperatures, eliminating all thermal motion, quantum mechanical zero-point motion would remain. The blades would still vibrate, however faintly, because the uncertainty principle won't let them be perfectly still. The quantum vacuum is like that. From a distance, at the scale of everyday life, it looks empty. It appears to be nothing at all. Perfectly still, perfectly calm, perfectly devoid of content. But zoom into the quantum scale, and the fields are jittering. Not because something is shaking them from outside, not because energy is being added. They jitter because quantum mechanics requires it. Perfect stillness at the quantum level is not merely difficult to achieve, it is impossible. Nature forbids it. This picture of the vacuum as a physical field state, rather than literal nothingness, is not a philosophical position. It's not a matter of interpretation or perspective, or how you choose to think about things. It's built into the mathematics of quantum field theory, the most precisely tested theoretical framework in all of science. The predictions of quantum field theory have been confirmed experimentally to accuracies of better than 1 part in 10 billion. No other theory in the history of science has been tested to this level of precision and survived. When this theory tells us that the vacuum is not empty, that it's a physical state of underlying fields with real, measurable properties, we have very strong reasons to take that seriously. Because every other prediction this framework has ever made has turned out to be correct. And this is the foundation for everything that follows. Once you understand that the vacuum is not nothing, once you truly see that so-called empty space is actually the ground state of quantum fields filling every point in the universe, the question of how particles can appear from the vacuum stops sounding mysterious and starts sounding almost natural. The fields are already there. The potential for excitation is already present at every point. What you need are the right conditions, extreme enough conditions, to promote those quiet ground state fluctuations into real, observable, detectable particles. The energy has to come from somewhere, and, as we'll see, it always does. But the raw material, the fields themselves, the substrate from which particles are made, is present everywhere. At all times, in every corner of the cosmos. The vacuum is not the absence of physics. It is where physics begins. So the vacuum is not nothing. It's the ground state of quantum fields, filled with irreducible activity demanded by the uncertainty principle. That much is established. But knowing the vacuum is not empty raises an immediate question. If the fields are constantly fluctuating, if they can never be perfectly still, what does that actually do? Does this restless activity have consequences? Can you detect it? Can you measure it? Or is it just an abstract mathematical feature of the theory, real on paper, but invisible in practice? The answer is that vacuum fluctuations have real, measurable physical effects. They produce forces between objects. They shift the energy levels of atoms. They modify the magnetic properties of electrons. These are not subtle philosophical implications that require careful interpretation. They are concrete, quantitative predictions that have been confirmed by experiments to extraordinary precision. The vacuum does things. And understanding what it does is essential before we can understand how it creates particles. Let's start with what the fluctuations actually look like, physically speaking. Remember that a quantum field exists at every point in space. In its ground state, the field has an average value of 0 at every point. No net excitation, no particles. But the uncertainty principle prevents the field from sitting exactly at 0 with exactly 0 rate of change. So the field value at any given point jiggles around 0, sometimes slightly positive, sometimes slightly negative, oscillating rapidly and randomly. Now, here's what's important. These fluctuations happen at all scales simultaneously. The field jiggles with very short wavelength oscillations and very long wavelength oscillations, and everything in between, all at once. Each wavelength contributes its own 0-point energy. When you add up all the contributions from all possible wavelengths, you get the total 0-point energy of the field. At every single point in space, these oscillations are happening, overlapping, interfering with each other in a continuous quantum buzz. Under normal conditions, this buzz doesn't produce detectable particles. The fluctuations are too brief and too small. They don't have enough energy concentrated in one place for long enough to create a stable excitation, which is what a real particle would be. The field jiggles, but it jiggles around its ground state. It's restless, but it's not excited enough to create anything lasting. Think of a pot of water at room temperature. The molecules are in constant thermal motion, jostling and vibrating. Occasionally, a molecule near the surface might bounce upward with enough energy to briefly leave the liquid. But under normal conditions, the water doesn't boil. The thermal energy isn't concentrated enough or sustained enough to produce a vigorous phase transition. The molecules are busy, but the water remains liquid. Similarly, the quantum fields in the vacuum are busy. They fluctuate constantly. But under ordinary conditions, those fluctuations remain below the threshold needed to produce real, observable particles. The vacuum buzzes, but it doesn't spark, at least not without help. Now, you may have heard a different description of vacuum fluctuations, one involving so-called virtual particles. The popular version goes something like this. The vacuum is filled with particles and antiparticles that constantly pop into existence from nothing, exist for a tiny fraction of a second, and then annihilate each other and vanish. They borrow energy from the vacuum, exist briefly, and pay it back before anyone notices. The vacuum is a seething ocean of these ghostly particles, flickering in and out of reality at every point in space. This picture is extraordinarily common. You'll find it in popular science books, magazine articles, documentaries, and even in some physics textbooks aimed at general audiences. And it captures a grain of truth. But it's also deeply misleading if taken literally, and understanding why it's misleading is critical for understanding what the vacuum actually does and how real particle creation works. Virtual particles are not tiny physical objects briefly materializing in empty space. They are a mathematical tool. Specifically, they arise in a calculation technique called perturbation theory, which physicists use to compute the probabilities of quantum processes. When you want to calculate, say, the probability that two electrons will scatter off each other, you can't solve the equation exactly. The mathematics is too complicated. Instead, you break the calculation into a series of increasingly complex contributions, each one represented by a diagram called a Feynman diagram, named after physicist Richard Feynman, who developed this approach in the late 1940s. In these diagrams, the real particles, the ones that actually exist before and after the interaction, are drawn as lines coming in from the edges. But the interaction between them is represented by internal lines connecting the real particles. These internal lines are the virtual particles. They're not observed. They don't appear in any detector. They exist only inside the calculation as intermediate mathematical terms. A virtual photon, for instance, represents a specific mathematical contribution to the force between two charged particles. It's a term in an equation. It's not a tiny flash of light materializing in empty space. Here's an analogy that might help. When you calculate a complex financial transaction, you might introduce intermediate variables. You might say, let x equal the pre-tax total and y equal the discount rate, and then combine x and y to get the final price. X and y are useful for organizing the calculation, but they're not separate real transactions. No money actually moves into an account labeled X and then out again. The intermediate variables are bookkeeping tools. They help you get the right answer, but they don't correspond to separate physical events. Virtual particles work the same way. They're intermediate terms in a perturbative calculation. They help physicists organize extremely complex mathematics and arrive at correct predictions. But they don't correspond to individual physical events happening at specific times and places in the vacuum. The vacuum fluctuations are real. The jittering of the quantum fields is real. But describing that jittering as tiny particles popping in and out of existence is an interpretation layered on top of a specific mathematical technique. It's not the only way to describe what's happening, and in many situations, it's not the best way. This distinction matters because the pop science picture of virtual particles leads to serious misunderstandings. It makes people think particles are literally appearing from nothing and vanishing, which sounds like energy conservation is being violated willy-nilly. It makes people think the vacuum is creating and destroying matter constantly, which sounds like something from nothing magic. And it makes people think that particle creation from the vacuum is just an amplified version of this constant popping, which misses the actual physics of how real particle creation works under extreme conditions. The reality is more subtle and more interesting. The vacuum fluctuates because the uncertainty principle demands it. Those fluctuations have measurable consequences, but describing those consequences as virtual particles materializing and annihilating is a metaphor borrowed from one particular calculation technique, not a literal description of physical events. The fields jitter. The jittering has effects. That's the physical content. The particle language is a convenient shorthand that can be helpful or harmful depending on how literally you take it. So what are the measurable consequences? Let's talk about the most famous one, the Casimir effect. In 1948, Dutch physicist Hendrik Casimir made a remarkable prediction. He calculated that if you take two flat, perfectly conducting metal plates and place them very close together in a vacuum, with nothing between them, no air, no radiation, no particles of any kind, there should be a measurable force pushing the plates toward each other. Not gravity, not electrostatic attraction, not magnetism. A force arising purely from the quantum fluctuations of the electromagnetic field in the vacuum between and around the plates. How does this work? Remember that the electromagnetic field fluctuates at all wavelengths simultaneously. Outside the plates, in the open space around them, there's no restriction on which wavelengths can exist. The field fluctuates freely at every wavelength, from the tiniest to the largest. But between the plates, there's a constraint. The plates are conducting, which means the electromagnetic field must satisfy specific conditions at their surfaces. Only certain wavelengths fit between the plates, wavelengths that match the gap. Other wavelengths are excluded. They simply can't exist in that confined space. Think of it like sound waves in a pipe. An organ pipe can support only certain sound wavelengths, those that fit neatly inside the pipe with the right boundary conditions. Other wavelengths are suppressed. Similarly, the gap between the Casimir plates acts as a filter. It allows some electromagnetic field modes and blocks others. The result is that the vacuum fluctuations between the plates are slightly weaker than the vacuum fluctuations outside the plates. There are fewer field modes between the plates, which means less zero-point energy per unit volume in that region. The energy density outside is higher than the energy density between. This imbalance creates a net force pushing the plates together, because the system can lower its total energy by reducing the gap. Casimir calculated the magnitude of this force. For plates separated by a distance of about 1 micrometer, roughly 100 times smaller than the width of a human hair, the pressure is extremely small, about 100,000th of atmospheric pressure. Tiny, but measurable. For decades after Casimir's prediction, the effect was too small to confirm experimentally. The plates needed to be extraordinarily close and extraordinarily flat. Any imperfection, any dust, any vibration would overwhelm the signal. But in 1997, physicist Steve Lamoureux performed the first precision measurement of the Casimir force using a gold-coated plate and a gold-coated sphere. His results matched Casimir's theoretical prediction to within 5%. Since then, numerous experiments have refined the measurement. The agreement between theory and experiment is now excellent, typically within 1 to 2%. This is one of the most direct demonstrations that the vacuum has physical properties. There is literally nothing between the plates. No matter, no radiation, no particles. Just the quantum fields in their ground state. And yet, a measurable force appears. The vacuum is not inert. It pushes, it pulls, it exerts forces on physical objects. All because the ground state fluctuations of the electromagnetic field are modified by the presence of the plates. The Casimir effect is sometimes described using virtual particle language. You might hear that the plates restrict which virtual photons can exist between them, creating an imbalance in virtual photon pressure. This description gives the right answer and can be a useful way to think about it. But it's important to remember that the fundamental physics is about field modes and zero-point energy, not about literal tiny photons bouncing between the plates. The field mode description is more general and less likely to create misunderstandings about what the vacuum actually does. The second major experimental confirmation of vacuum field activity involves the energy levels of hydrogen, the simplest atom in the universe. This is the Lamb shift, and its discovery was one of the pivotal moments in the history of quantum physics. In 1947, Willis Lamb and Robert Rutherford performed a careful experiment measuring the energy levels of hydrogen. According to Dirac's theory of the electron, two specific energy states of hydrogen, known as the 2s½ and 2p½ states, should have exactly the same energy. Dirac's equation, which was the best available theory at the time, predicted that these two states were perfectly degenerate, meaning identical in energy. But Lamb and Rutherford found that the two states were not identical. The 2s½ state had slightly more energy than the 2p½ state. The difference was tiny, corresponding to a frequency of about 1057 MHz, a microwave frequency. But it was real and reproducible. Something was shifting the energy level of one state relative to the other, and Dirac's equation couldn't account for it. The explanation turned out to involve the vacuum. Specifically, it involved the interaction between the electron in the hydrogen atom and the fluctuating electromagnetic field of the vacuum. Even though there are no real photons present inside the atom under normal conditions, the zero-point fluctuations of the electromagnetic field affect the electron's motion. The fluctuating field gives the electron a slight random jitter, causing it to explore a slightly larger region of space than it otherwise would. This jitter modifies the electron's interaction with the proton's electric field, slightly shifting its energy. The 2s½ state is more affected than the 2p½ state, because the 2s½ state has a higher probability of the electron being very close to the proton, where the proton's electric field is strongest and where the jitter has the largest effect. The result is a small but measurable difference in energy between the two states, exactly as Lamb and Rutherford observed. This calculation was one of the first great triumphs of quantum electrodynamics, the quantum field theory of electromagnetism. Shinichiro Tomonaga, Julian Schwinger, and Richard Feynman independently developed the mathematical techniques needed to calculate such effects precisely. Their work earned them the Nobel Prize in 1965, and the Lamb shift remains one of the most precisely measured quantities in all of physics. The agreement between the theoretical prediction and the experimental measurement is extraordinary, accurate to better than 1 part in a million. Think about what this means. The energy levels of the simplest atom in the universe are affected by the fluctuations of quantum fields in the vacuum. The vacuum is not a passive backdrop for atomic physics. It actively participates. It shifts energy levels. It modifies physical properties. Even the most basic atom in nature carries the fingerprint of vacuum activity in its energy structure. There's yet another effect worth mentioning, and in many ways it's the most striking of all. The anomalous magnetic moment of the electron. Every electron behaves like a tiny magnet, with a property called a magnetic moment. Dirac's equation predicts a specific value for this magnetic moment, but when physicists measured it with extreme precision, they found it was slightly different from Dirac's prediction, slightly larger. The discrepancy, about 0.1%, comes from the electron's interaction with vacuum fluctuations. To understand what's happening physically, you need to appreciate that no particle in the universe exists in isolation. An electron is an excitation of the electron field, but the electron field doesn't exist in a sealed room by itself. It coexists with the electromagnetic field, the muon field, the quark fields, all of them overlapping at every point. And because these fields are all fluctuating in their ground states, the electron is constantly interacting with the quantum noise of the vacuum around it. In the language of Feynman diagrams, the electron constantly emits and reabsorbs virtual photons. Those virtual photons can briefly split into virtual electron-positron pairs, which interact with more virtual photons, and so on in an ever-expanding cascade of increasingly complex contributions. Each contribution modifies the electron's observed properties slightly. The electron you actually measure in an experiment is not a bare electron, a clean, isolated excitation of the electron field with no vacuum interactions. It's a dressed electron, an excitation that comes inseparably bundled with a cloud of vacuum field activity surrounding it at all times. This distinction between the bare electron and the dressed electron is one of the most important conceptual insights in quantum field theory. The bare electron, the one described by Dirac's original equation, has specific properties, a specific magnetic moment, a specific charge, a specific mass. But you never observe the bare electron. You can't strip away the vacuum interactions to see what the electron looks like naked, because the vacuum is everywhere. There's nowhere to go where the quantum fields aren't fluctuating. Every measurement you make of an electron includes the vacuum's contribution. The properties you measure, the magnetic moment, the charge, even the mass, are always the dressed values, the values that include the effect of the vacuum's constant activity. When physicists calculated the correction to the electron's magnetic moment using quantum electrodynamics, including contributions from more and more complex Feynman diagrams, the theoretical prediction matched the experimental measurement to more than 10 significant digits. This is often cited as the most precise agreement between theory and experiment in the history of science. The measured value of the electron's anomalous magnetic moment agrees with the quantum electrodynamics calculation to better than 1 part in 10 billion. 1 part in 10 billion. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. And this prediction depends crucially on vacuum fluctuations. Without the effects of the fluctuating vacuum fields, the theoretical value would be wrong. The vacuum's activity is not optional, it's required. Without it, the most precisely tested prediction in physics would fail. Every particle you've ever encountered, every electron in every atom in your body, carries the imprint of the vacuum in its measured properties. The vacuum doesn't just surround particles, it dresses them, it shapes them, it makes them what they are. Now, there's an important point that gets lost in many popular accounts of vacuum fluctuations, and it concerns energy conservation. Because when people hear about the vacuum buzzing with activity, about fields jittering and fluctuations having physical effects, a natural question arises. Where does the energy come from? If the vacuum is doing things, exerting forces, shifting energy levels, where is it getting the energy to do that? Is energy conservation being violated? The answer is no. Energy conservation is not violated. But the situation is more nuanced than it might first appear, and understanding the nuance is important. The zero-point energy of the vacuum is not energy that was added to the fields from some external source. It's not energy that appears and disappears. It's the minimum energy the fields can have, built into their quantum nature. You can think of it as the energy cost of the uncertainty principle. Quantum mechanics requires the fields to fluctuate, and fluctuation requires energy. That energy is permanently present in the ground state. It's not borrowed, it's not temporary, it's simply the lowest energy the system can have. You've probably encountered a related idea in the context of virtual particles, the so-called energy-time uncertainty relation. This is often stated as delta E times delta T is approximately equal to, or greater than, Planck's constant divided by 2 pi. The popular interpretation goes like this. You can borrow an amount of energy, delta E, from the vacuum, as long as you pay it back within a time, delta T. The larger the energy you borrow, the faster you must return it. Virtual particles borrow energy, briefly exist, and then return the energy when they annihilate. This story is not quite right. The energy-time uncertainty relation is real, but it doesn't mean energy conservation is temporarily suspended. The relation describes a fundamental limit on how precisely you can measure energy in a finite time interval. If you observe a system for only a brief period, you cannot determine its energy with arbitrary precision. The energy appears uncertain, not because it's actually fluctuating in violation of conservation, but because the measurement process itself has a fundamental limitation. In quantum field theory, the vacuum state has a perfectly well-defined energy. It's the ground state energy, and it doesn't change with time. The fluctuations of the fields are not violations of energy conservation happening moment to moment. They're the intrinsic quantum uncertainty in the field values, consistent with a fixed total energy. The vacuum is in an energy eigenstate. Its energy is definite. What's uncertain are the field values at individual points, not the total energy of the system. This is a subtle but critical distinction. The vacuum fluctuates, yes, but it fluctuates within a state of fixed energy. The 0-point energy is constant. It doesn't increase or decrease as the fields jitter. The fluctuations are a property of the quantum state, not a process that creates and destroys energy. Nothing is being borrowed and repaid. The energy is simply there, permanently, as a feature of the ground state. When the Casimir effect produces a force between two plates, the energy comes from the change in the vacuum's total 0-point energy caused by moving the plates. When you bring the plates closer together, you exclude certain field modes from the gap. The total 0-point energy decreases because fewer modes exist. The energy difference shows up as the force pulling the plates together. Energy is conserved throughout. The force isn't free energy from nowhere. It's a redistribution of vacuum energy caused by changing the boundary conditions. When the Lamb shift modifies the energy levels of hydrogen, the energy comes from the interaction between the electron and the vacuum electromagnetic field. The vacuum field's 0-point fluctuations couple to the electron, modifying its energy. But the total energy of the system, electron plus vacuum field, is conserved. Nothing appears from nowhere, nothing is borrowed. The vacuum field and the electron exchange energy in a way that shifts the measured energy levels, but the total is always accounted for. This is why the popular picture of particles constantly popping in and out of existence, borrowing energy from the void and returning it before anyone notices, is so misleading. It implies that energy conservation is being casually bent, stretched, temporarily violated in a wink and nod sort of way. But that's not what happens. Energy conservation holds rigidly at all times in all quantum processes. The vacuum's activity is not a violation of conservation. It is consistent with conservation. The fluctuations occur within a state of definite energy. They're a feature of the quantum ground state, not evidence that the rules of physics are being broken. This point matters enormously when we turn to real particle creation, because one of the biggest misconceptions about the vacuum-producing particles is that it's somehow getting something for nothing, that particles are appearing from nowhere with no energy source, that the universe is casually creating matter from the void. This is not what happens. When the vacuum produces real particles, There is always an energy source. Always. Whether it's an intense electromagnetic field, or the gravitational energy near a black hole, or the expansion of space itself, something is providing the energy that gets converted into the mass and kinetic energy of the new particles. The fields are already there. The potential for excitation is already present. But the energy to promote those quiet fluctuations into real particles must come from somewhere specific and identifiable. So let's take stock of where we are. The vacuum is not empty. It's the ground state of quantum fields that fill all of space. Those fields fluctuate because the uncertainty principle demands it. The fluctuations are real and have been confirmed by multiple independent experiments: the Casimir effect, the Lamb shift, the anomalous magnetic moment of the electron, among others. These experiments agree with theoretical predictions to spectacular precision, in some cases to better than 1 part in 10 billion. The fluctuations do not violate energy conservation. They occur within a state of fixed, definite energy. And the popular picture of virtual particles constantly appearing and vanishing, while useful as a rough metaphor, is more a feature of a specific mathematical technique than a literal description of physical events. The vacuum is active. It has physical consequences. It exerts forces, shifts energies, and modifies the properties of every particle in the universe. But under normal conditions, this activity stays below the threshold of producing real, lasting, detectable particles. The fields jitter, but they don't spark. The fluctuations are there, but they remain in the ground state. Nothing observable emerges until you change the conditions, until you impose something extreme enough, powerful enough, violent enough to push those quiet fluctuations over the edge. And when you do, when the right external conditions are present, the vacuum stops merely buzzing and starts producing real particles, detectable particles, particles with mass and charge and momentum that can be measured by instruments and recorded by detectors and studied by physicists. Not virtual, not temporary, not mathematical bookkeeping. Real. That is what happens under extreme conditions, and the mechanisms by which it happens are among the most extraordinary predictions in all of physics. Everything we've discussed so far has been about the vacuum under ordinary conditions. Fields fluctuating in their ground state, measurable effects like the Casimir force and the Lamb shift. Real physics, confirmed by experiment, but physics in which no lasting particles emerge from the vacuum. The fluctuations stay below the threshold. The fields jitter, but they don't produce anything you could catch in a detector and call a particle. Now we cross into different territory, because there are physical situations, extreme situations, involving enormously powerful fields, violent accelerations, or the warped space-time near black holes, where the vacuum is pushed past its threshold. The quiet ground state fluctuations get amplified, distorted, and driven so far from equilibrium that the fields cross over into genuinely excited states. Real particles appear. Not virtual, not temporary mathematical terms in a perturbative expansion. Actual particles with mass, charge, and momentum. Particles that travel away from their point of origin, strike detectors, and leave permanent records. This is not something from nothing. In every case, there is a specific, identifiable source of energy driving the process. The vacuum provides the field substrate, the raw material. But the energy to excite those fields into particle states comes from outside, from whatever extreme condition is doing the pushing. An electric field, a gravitational field, an acceleration. Something physical supplies the energy. The vacuum converts it into matter. Let's begin with the most conceptually straightforward case, the Schwinger effect. Imagine empty space, true vacuum, with nothing in it. No particles, no radiation, just quantum fields in their ground state. Now switch on an electric field. Not a weak one, not the kind you'd get from a battery or a power line or even a lightning bolt. An electric field of almost unimaginable intensity. We're talking about a field strength on the order of 10 to the 18 volts per meter. That's roughly a billion volts across a single meter of space. Nothing like this exists in everyday life. The strongest electric fields humans can produce in laboratories are still many orders of magnitude weaker. But in principle, and in certain extreme astrophysical environments, such fields can exist. And when they do, something extraordinary happens. The electron field, which pervades all of space in its ground state, responds to the electric field. Remember, the electron field is always there. Its fluctuations are always present. Under normal conditions, those fluctuations don't produce real electrons because there's not enough energy concentrated in the right way to create stable excitations. But when you apply an electric field of sufficient strength, the situation changes dramatically. Here's the physical picture. In quantum mechanics, there is a phenomenon called quantum tunneling. A particle that doesn't have enough energy to climb over a barrier can sometimes pass through it instead, appearing on the other side as though it had walked through a wall. This happens because quantum particles don't have definite positions. They're described by probability waves, and those waves don't stop abruptly at the edge of a barrier. They extend into and sometimes through the barrier, decaying as they go. If the barrier is thin enough, or the particle's wave function extends far enough, there is a real probability of the particle appearing on the other side. The Schwinger effect is a kind of tunneling process, but instead of a particle tunneling through a physical wall, it involves the vacuum tunneling into a state containing real particles. In the absence of any external field, there is an energy barrier separating the vacuum from a state containing an electron-positron pair. That barrier exists because creating a pair requires energy, at minimum twice the rest mass energy of an electron, which is about 1 million electron volts. Under normal conditions, the barrier is insurmountable. The vacuum stays in its ground state. But an intense electric field changes the shape of this barrier. It tilts the energy landscape, effectively thinning the barrier. The stronger the field, the thinner the barrier becomes. And when the barrier becomes thin enough, quantum tunneling through it becomes probable. The vacuum tunnels from its ground state into a state containing real electron-positron pairs. The pairs appear not because something gave them a sudden kick of energy, but because the electric field has reshaped the energy landscape so thoroughly that the vacuum's own quantum nature allows it to transition into a particle-containing state. The electric field does work on the newly created particles as they separate, accelerating the electron in one direction and the positron in the opposite direction. The energy for this comes from the electric field itself, which loses energy in the process. This is entirely consistent with energy conservation. The electric field provides the energy, the vacuum provides the field substrate, and the result is a real electron and a real positron flying apart in opposite directions, accelerated by the very field that created them. This effect was first analysed theoretically by Fritz Zorter in 1931, building on Dirac's theory of the electron, and was placed on rigorous mathematical footing by Julian Schwinger in 1951. Schwinger calculated the precise rate at which electron-positron pairs should be produced as a function of the electric field strength. His result showed that the production rate is extraordinarily sensitive to the field strength. Below a critical threshold, now called the Schwinger limit, the rate is so vanishingly small that you would wait longer than the age of the universe to see a single pair produced. Above the threshold, the rate increases exponentially, and pairs begin pouring out of the vacuum in enormous numbers. The Schwinger limit for electron-positron production is approximately 1.3 times 10 to the 18 volts per meter. This is an extraordinarily intense field. To put it in perspective, the strongest sustained electric fields produced in modern laboratories are roughly 10 to the 12 volts per meter, about 1 million times too weak. Even the most powerful laser facilities in the world, facilities designed specifically to push the boundaries of field intensity, are still a few orders of magnitude short of the Schwinger limit. So the Schwinger effect has never been directly observed in a laboratory. Not yet. But physicists believe it's real, and for very good reason. The same theoretical framework that predicts the Schwinger effect also predicts the Lamb shift, the Casimir effect, and the electron's anomalous magnetic moment, all of which have been confirmed to spectacular precision. There's no reason to doubt the Schwinger prediction if you trust the framework that makes it. And that framework has earned trust through a century of unbroken experimental success. Moreover, there are astrophysical environments where fields approaching the Schwinger limit may exist. Near certain types of neutron stars called magnetars, magnetic field strengths can reach 10 to the 11 Tesla, which corresponds to electric field effects in the range relevant to pair production. Some physicists believe that Schwinger-type pair creation may actually occur in the extreme environments around these objects, producing electron-positron pairs from the vacuum of space surrounding the star. The energy comes from the star's ferocious magnetic field. The vacuum provides the electron field, and real matter appears in a region where, a moment before, there was nothing but empty space and an intense field. Now let's move to something even stranger, the Unruh effect. In 1976, physicist William Unruh made a remarkable theoretical discovery. He showed that an observer accelerating through the vacuum of empty space would detect real particles, even though an observer at rest in the same region of space would detect nothing at all. The vacuum that looks perfectly empty to one observer looks filled with a warm bath of particles to another, depending purely on how the observer is moving. This sounds impossible. Either there are particles or there aren't. How can the answer depend on who's asking? But in quantum field theory, the answer genuinely does depend on the observer's state of motion. And the reason cuts to the heart of what particles actually are. Remember, particles are excitations of quantum fields. What counts as the ground state, the vacuum, depends on how you define your energy levels. And that definition depends on your reference frame. A freely floating observer in empty space defines the vacuum as the state with no particles. This is the standard vacuum, the ground state we've been discussing throughout this script. But an observer who is constantly accelerating experiences space-time differently. The acceleration changes the relationship between the observer and the quantum fields. It distorts the way the observer interacts with field modes, filtering them in a way analogous to how the Casimir plates filter the electromagnetic field. The result is that the accelerating observer's detector clicks. It registers particles. Specifically, it registers a thermal bath of particles, a gas of particles with a specific temperature that depends on the magnitude of the acceleration. The higher the acceleration, the higher the temperature, and the more particles the observer detects. The Unruh temperature is given by a precise formula relating the acceleration to a temperature. For the temperatures to be detectable by any current instrument, the acceleration would need to be absurdly large, roughly 10 to the 20 meters per second squared, about a billion times the acceleration due to gravity on Earth's surface. At such accelerations, the Unruh temperature would be about 1 Kelvin, just 1 degree above absolute zero. Still cold, but in principle measurable. At more modest accelerations, the temperature is so incredibly tiny that no existing detector could possibly register it. Because of this, the Unruh effect has not been directly observed. The accelerations required are far beyond anything achievable in a laboratory. You would need to accelerate a detector so violently that no known material could survive the forces involved. But, like the Schwinger effect, the Unruh effect is predicted by the same quantum field theory framework that has been confirmed in countless other contexts. And it reveals something profound about the nature of particles and the vacuum. The Unruh effect tells us that the particle content of space is not absolute. It's observer-dependent. The vacuum itself is not a universal concept on which all observers agree. One observer's empty space is another observer's thermal bath of particles. This does not mean reality is subjective or that physics is arbitrary. The underlying quantum field state is the same for both observers. What differs is how each observer interacts with that state, how each one defines particles, and what each one's detector is sensitive to. The field is the fundamental reality. Particles are how specific observers experience the field, and different observers, moving in different ways, can experience the same field differently. Where does the energy come from? It comes from whatever is causing the acceleration. If you're strapped to a rocket accelerating at tremendous speed, the rocket engine is burning fuel and converting chemical energy into kinetic energy. Some of that energy goes into accelerating you and the detector, but some of it, according to the Unruh effect, effectively goes into the particles that your detector registers. The energy is not appearing from the vacuum for free. It's being supplied by the source of acceleration. The vacuum field converts the kinetic energy of acceleration into thermal particle excitations, as experienced by the accelerated observer. Energy conservation holds. The rocket pays the bill. This brings us to the most famous case of all, the one that captured the imagination of physicists and the public alike when it was first proposed: Hawking radiation. In 1974, Stephen Hawking published a calculation that shocked the physics community. He showed that black holes are not perfectly black. They radiate. A black hole, an object whose gravitational field is so intense that not even light can escape from within its event horizon, nevertheless emits a steady, faint glow of particles from the region just outside that horizon. The black hole gradually loses mass and energy through this radiation. Given enough time, without any matter falling in to replenish it, a black hole would eventually evaporate completely, shrinking away to nothing. This was astonishing. Black holes were supposed to be the ultimate cosmic dead ends. Once something falls past the event horizon, it's gone forever. Nothing comes back out. That was the classical picture from general relativity. Hawking showed that quantum field theory changes this picture in a fundamental way. The mechanism behind Hawking radiation is closely related to the Unruh effect, and both are rooted in the same underlying physics of quantum fields in curved or distorted spacetime. Near a black hole's event horizon, spacetime is intensely curved by the black hole's gravitational field. This curvature distorts the vacuum state of the quantum fields in the region. What looks like a vacuum, a ground state with no particles, to an observer freely falling through the horizon, looks like a state filled with real thermal particles to an observer hovering at a safe distance outside the hole. Here's a more detailed way to understand what happens. Far from the black hole, spacetime is approximately flat, and the vacuum state of the quantum fields is the standard one we've been discussing, the quiet ground state with nothing but zero-point fluctuations. But near the event horizon, the gravitational field is so strong that it dramatically warps the structure of spacetime. This warping changes what the ground state looks like. The field modes near the horizon are stretched and distorted by the curvature. Modes that would have been part of the quiet ground state in flat spacetime get mixed and scrambled by the gravitational field. The result is that a distant observer, far from the black hole, looking toward the horizon, detects a steady stream of particles radiating outward. These particles have a thermal spectrum, meaning they look exactly like radiation from a hot object. The temperature of this radiation depends on the mass of the black hole. Smaller black holes are hotter, larger black holes are cooler. For a black hole with the mass of our Sun, the Hawking temperature is about 60 billionths of a Kelvin. That's absurdly cold, trillions of times colder than the cosmic microwave background radiation that fills all of space. Such a black hole radiates so feebly that its Hawking radiation is completely undetectable with any foreseeable technology. But the principle is what matters. The gravitational field of the black hole is doing work on the quantum fields near the horizon, distorting them so severely that the vacuum state, as defined by a distant observer, contains real particles. Those particles carry energy away from the black hole, and that energy comes from the black hole itself. As the black hole radiates, it loses mass. Its event horizon shrinks. The black hole gets smaller, hotter, and radiates faster. This is a runaway process. A black hole losing mass through Hawking radiation radiates more intensely as it shrinks, which makes it lose mass faster, which makes it radiate even more intensely. Eventually, in the final moments of a black hole's life, the radiation becomes extraordinarily intense as the remaining mass is converted into a final burst of particles and energy. For a solar mass black hole, this process takes an almost incomprehensible amount of time, roughly 10 to the 67 years, vastly longer than the current age of the universe, which is only about 13.8 billion years. So no stellar black hole anywhere in the cosmos has come close to evaporating through Hawking radiation. But for hypothetical microscopic black holes, if they exist, the evaporation would be much faster because smaller black holes are hotter. A black hole with a mass of about 1 trillion kilograms, roughly the mass of a small mountain, would have a temperature of about 100 billion Kelvin and would evaporate in roughly the current age of the universe. Such a black hole, if it existed, might be detectable through its Hawking radiation today. Where does the energy come from? This is a question people often ask about Hawking radiation, and the answer is important because it reinforces the central point that particle creation from the vacuum is never free. The energy comes from the gravitational field of the black hole. As particles radiate away, they carry energy with them. That energy is extracted from the black hole's gravitational field. The black hole's mass decreases accordingly. The total energy, black hole mass energy plus radiated particle energy, is conserved throughout. Nothing is created from nothing. The gravitational field provides the energy, the quantum fields provide the substrate, and the extreme curvature of spacetime near the horizon provides the mechanism that converts one into the other. Jacob Bekenstein had shown in the early 1970s that black holes have entropy, a measure of disorder proportional to the area of their event horizon. Hawking's discovery of black hole radiation confirmed that black holes also have temperature, completing the thermodynamic picture. Black holes aren't just gravitational objects, they're thermodynamic systems with temperature, entropy, and energy, obeying laws analogous to the laws of thermodynamics. This connection between gravity, quantum mechanics, and thermodynamics is one of the deepest and most surprising in all of physics, and it traces directly back to the fact that the vacuum can produce particles under extreme gravitational conditions. Now, there's a fourth effect that deserves attention, because unlike the Schwinger effect, the Unruh effect, and Hawking radiation, this one has actually been observed in a laboratory. It's called the dynamical Casimir effect, and it represents the closest anyone has come to directly watching the vacuum produce real particles under controlled conditions. Remember the static Casimir effect from earlier? Two metal plates placed close together in a vacuum experience a force because the plates restrict which electromagnetic field modes can exist between them. That was about the vacuum exerting a force. The dynamical version is about the vacuum creating particles. The idea is straightforward in principle. If you take a mirror, a boundary that reflects electromagnetic waves, and move it fast enough, the mirror's motion disturbs the vacuum fluctuations of the electromagnetic field. As the mirror accelerates, it changes the boundary conditions for the field modes, and those changing conditions can pump energy into the vacuum's ground state fluctuations, promoting them into real photons. The mirror literally shakes particles out of the vacuum. You can think of it this way. The vacuum fluctuations are always present, always jittering. Normally, the field modes on either side of a stationary mirror are in equilibrium. Nothing happens. But if the mirror accelerates violently, it disrupts that equilibrium. The field modes that existed a moment ago are no longer the right modes for the new mirror position. The field has to readjust, and in doing so, some of the vacuum's zero-point energy gets converted into real photons that fly away from the mirror. The energy comes from whatever is driving the mirror's motion. The vacuum provides the electromagnetic field substrate. and the photons that emerge are real, detectable, and carry energy and momentum. The problem is that to produce a detectable number of photons this way, the mirror would need to move at a significant fraction of the speed of light. No physical mirror can do that. The forces required would destroy any material long before it reached the necessary speeds. For decades, the dynamical Casimir effect seemed destined to remain as theoretical as Hawking radiation, a prediction too extreme to test. But in 2011, a team of physicists at Chalmers University of Technology in Sweden found a way around this limitation. Instead of moving a physical mirror, they used a superconducting electrical circuit to simulate a mirror moving at roughly 5% of the speed of light. The device used a component called a superconducting quantum interference device, which could change the effective boundary conditions for microwave photons in the circuit at extraordinary speeds, billions of times per second. This mimicked a mirror oscillating back and forth at velocities no physical object could actually achieve. The result was exactly what theory predicted. Real microwave photons appeared in the circuit, emerging from what had been the vacuum state of the electromagnetic field. The photons had the right statistical properties, the right energy spectrum, the right correlations. They matched the predictions of quantum field theory precisely. The vacuum had produced real, detectable particles in a laboratory setting. This was a landmark experiment. It was the first direct observation of real particles being created from the vacuum by rapidly changing boundary conditions. Not a force between plates, not a shift in atomic energy levels. Actual photons, shaken loose from the ground state of the electromagnetic field by the rapid motion of an effective mirror. The vacuum had sparked. The dynamical Casimir effect connects beautifully to the other three mechanisms we've discussed. In every case, an external condition, be it an electric field, an acceleration, a gravitational field, or a rapidly moving boundary, distorts the vacuum in a way that converts ground state fluctuations into real particles. The dynamical Casimir effect is the most accessible example, the one closest to laboratory conditions, and the only one that has been confirmed by direct experiment. Now, let's step back and look at what all four of these effects have in common. The Schwinger effect, the Unruh effect, Hawking radiation, and the dynamical Casimir effect are all examples of the same fundamental phenomenon. The vacuum of quantum field theory, the ground state of the quantum fields, being driven into an excited state by an external condition, producing real, detectable particles in the process. In each case, the mechanism is different. An intense electric field, a violent acceleration, the extreme curvature of space-time near a black hole, a rapidly oscillating boundary. But the underlying physics is the same. Quantum fields permeate all of space. Under normal conditions, they sit in their ground state, quietly fluctuating but not producing anything lasting. Under extreme conditions, an external influence distorts the vacuum state so severely that what was a ground state for one set of conditions becomes an excited state containing real particles for another. And in every single case, energy conservation is respected. The Schwinger effect draws energy from the electric field that creates the pairs. The Unruh effect draws energy from whatever source is causing the acceleration. Hawking radiation draws energy from the gravitational field of the black hole. The dynamical Casimir effect draws energy from whatever drives the mirror's motion. The vacuum is not a free lunch. It's not a source of unlimited energy. It's a field state that can be driven into excitation when sufficient energy is provided from an external source. The fields are the medium. The extreme conditions are the driver, and the particles are the result. This also clarifies why the loose pop science claim that particles are just constantly appearing from nothing in the vacuum is so misleading. Under ordinary conditions, the vacuum does not produce real particles. Full stop. The zero-point fluctuations are there, yes. The Casimir force is real, yes. But no lasting particles emerge from the vacuum of empty space under normal circumstances. Particle creation requires extreme conditions. It requires energy input from a specific source. It is a process governed by precise, calculable physics, not a vague handwave about mysterious quantum randomness making stuff appear for no reason. The vacuum can produce particles, but it does so only when pushed, only when the physics demands it, and only when the energy is supplied. That's not magic. That's a field responding to extreme stress. And it's one of the most remarkable consequences of the quantum nature of empty space. There's one more point worth emphasizing, because it captures something beautiful about this physics. The four effects we've discussed were discovered independently by different physicists working on different problems using different mathematical techniques. The Schwinger effect came from quantum electrodynamics and the study of strong electromagnetic fields. The Unruh effect came from the study of accelerated observers in flat spacetime. Hawking radiation came from the study of quantum fields near black holes in curved spacetime. The dynamical Casimir effect came from the study of time-dependent boundary conditions in quantum optics. And yet, when you look at the physics carefully, they're all connected. The Unruh effect and Hawking radiation in particular are deeply related. Near the event horizon of a black hole, the gravitational field creates an effective acceleration for static observers. An observer hovering just outside the horizon must accelerate intensely to avoid falling in. The equivalence principle of general relativity tells us that acceleration and gravity are locally indistinguishable. So an observer accelerating in flat spacetime, experiencing the Unruh effect, and an observer hovering near a black hole horizon, experiencing Hawking radiation, are in physically analogous situations. The particle production they detect has the same fundamental origin. The vacuum state is being distorted by the observer's relationship to the space-time geometry, and the distortion creates real particles. This deep connection between gravity, acceleration, and particle creation is one of the most profound insights of 20th century physics. It tells us that the vacuum, far from being inert and featureless, is exquisitely sensitive to the structure of space-time. Curve space-time enough, accelerate violently enough, apply strong enough fields, shake boundaries fast enough, and the vacuum responds. It responds by producing matter, by converting field energy into particles, by turning what was apparently nothing into something real and detectable. The vacuum is not passive. It is not inert. It is not nothing. It is a dynamic, responsive physical medium that participates actively in some of the most extreme processes in the universe. And every time it produces particles, it does so in a way that is completely consistent with energy conservation, completely consistent with the laws of quantum field theory, and completely devoid of magic. We've now seen what the vacuum is, what it does, and how it creates particles under extreme conditions. But there's a much larger question waiting. Why does any of this matter? Why should anyone, physicist or not, care that empty space is secretly a physical field state capable of producing matter? The answer is that the vacuum isn't just one curiosity among many in modern physics. It's foundational. The properties of the vacuum determine the structure of the universe, the kinds of particles that can exist, the forces that act between them, and ultimately, whether anything like stars, planets, or life is possible at all. Understanding the vacuum is not a side topic. It's one of the most important open frontiers in all of science. Let's start with the biggest stage imaginable, cosmology, the study of the universe as a whole. In 1917, Albert Einstein applied his general theory of relativity to the universe at large and encountered a problem. His equations predicted that the universe should be either expanding or contracting. It couldn't just sit still. But Einstein, like most scientists of his era, believed the universe was static, eternal, and unchanging on the largest scales. To fix this, he added a term to his equations, a constant he called the cosmological constant, represented by the Greek letter lambda. This term acted as a kind of repulsive pressure built into the fabric of space-time itself, counterbalancing gravity and allowing a static universe. When Edwin Hubble showed in 1929 that distant galaxies are moving away from us, proving the universe is expanding, Einstein reportedly called the cosmological constant his greatest blunder. He removed it from his equations. For decades, most physicists treated it as a historical footnote, an unnecessary complication that Einstein had introduced for the wrong reasons and then abandoned. But the cosmological constant came roaring back. In 1998, two independent teams of astronomers studying distant supernovae discovered something nobody expected. The expansion of the universe is not slowing down. It's speeding up. Galaxies are flying apart from each other at an accelerating rate. Something is pushing the universe apart, counteracting gravity on the largest scales, driving the expansion faster and faster over time. This mysterious something was given the name dark energy, and the simplest explanation for dark energy is, remarkably, Einstein's cosmological constant. A constant energy density filling all of space, inherent in the fabric of space-time itself, exerting a repulsive gravitational effect that pushes the universe to expand faster and faster. Now, here's where the vacuum enters the picture. Because if the vacuum of quantum field theory has energy, which it does as we've established, then that energy should contribute to the cosmological constant. The zero-point energy of all the quantum fields filling space should act as a source of gravity, or in this case, anti-gravity, influencing the expansion rate of the universe. The vacuum energy density and the cosmological constant are, in principle, the same thing. They describe the same physical quantity, the energy density of empty space. So physicists tried to calculate the vacuum energy density using quantum field theory. They added up the zero-point contributions from all the known quantum fields, and the number they got was catastrophically, absurdly, mind-bogglingly wrong. The calculated value of the vacuum energy density using straightforward quantum field theory is roughly 10 to the 120 times larger than the observed value. That's a 1 followed by 120 zeros. This is not a small disagreement. This is the largest discrepancy between theoretical prediction and experimental observation in the entire history of science. It's not even close to being close. The predicted value is so enormously larger than the observed value that something is clearly, fundamentally, deeply wrong with our understanding of how vacuum energy connects to gravity. This problem is called the vacuum catastrophe, or sometimes the cosmological constant problem, and it has been called the worst prediction in the history of physics. Not because physicists are bad at calculations, but because two of our most successful theoretical frameworks, quantum field theory and general relativity, give wildly incompatible answers when you try to combine them on this particular question. Quantum field theory tells us the vacuum has an enormous energy density. General relativity tells us that energy density should curve spacetime and drive cosmic expansion. But the observed expansion rate corresponds to a vacuum energy density that is essentially zero compared to what quantum field theory predicts. Something is cancelling almost all of the vacuum energy, leaving behind only a tiny residual that drives the observed accelerating expansion. But we have no idea what that something is. This is not a minor technical problem. It's one of the deepest unsolved questions in all of physics. It sits at the intersection of quantum mechanics and gravity, in the territory where we know our current theories are incomplete. Solving the cosmological constant problem would almost certainly require a breakthrough in our understanding of quantum gravity, the still unfinished theory that merges quantum mechanics with general relativity. It might require entirely new principles of physics that we haven't discovered yet. and it's intimately connected to the nature of the vacuum, because the problem is fundamentally about what the vacuum's energy actually does when gravity enters the picture. The dark energy that fills our universe, whatever it ultimately turns out to be, makes up about 68% of the total energy content of the cosmos. Ordinary matter, the atoms that make up stars, planets, and people, accounts for only about 5%. Dark matter, the invisible substance whose gravity holds galaxies together, contributes about 27%. The single largest component of the universe is the energy of empty space. The vacuum dominates the cosmic energy budget. Understanding it is not optional if we want to understand the universe. Now let's turn to another cosmological connection, one that takes us all the way back to the earliest moments of the universe. Because vacuum fluctuations didn't just shape the present cosmos, they shaped the past. They seeded the very structures we see in the sky tonight. In the first tiny fraction of a second after the Big Bang, the universe is thought to have undergone a period of extraordinarily rapid expansion called inflation. This idea, proposed by physicist Alan Guth in 1980, solves several deep puzzles about why the universe looks the way it does. Why is the universe so uniform in every direction? Why is its geometry so close to flat? Why don't we see certain exotic relics from the very early universe that many theories predict should exist? Inflation answers all of these by proposing that the universe expanded exponentially, doubling in size over and over again in a tiny fraction of a second, stretching a microscopic patch of space into something far larger than the observable universe today. But inflation does something else, something directly connected to everything we've been discussing. During inflation, the quantum fields filling space were fluctuating, just as they always do. 0-point jitter, ground state activity, the irreducible quantum noise demanded by the uncertainty principle. Under normal conditions, these fluctuations are microscopic. They happen at subatomic scales and stay at subatomic scales. But inflation was not normal conditions. Inflation was the most extreme expansion event in the history of the universe. And during that expansion, the microscopic quantum fluctuations in the fields were stretched to enormous scales. Fluctuations that started smaller than an atom were inflated to sizes spanning billions of light years. Quantum jitter became cosmic structure. These stretched-out fluctuations became tiny variations in the density of matter and energy across the early universe. Some regions ended up very slightly denser than average. Others ended up very slightly less dense. The differences were minuscule, about 1 part in 100,000. But gravity amplified them over billions of years. The slightly denser regions attracted more matter, grew denser still, and eventually collapsed under their own gravity to form galaxies, clusters of galaxies, and the vast cosmic web of filaments and voids that we observe in the universe today. This means the large-scale structure of the universe, the distribution of galaxies across billions of light years, traces its origin directly back to quantum vacuum fluctuations in the first fraction of a second after the Big Bang. The vacuum didn't just passively sit there while the universe formed around it. The vacuum's own quantum activity provided the seeds from which all cosmic structure grew. Without those fluctuations, the universe would be perfectly smooth. No clumps of matter, no galaxies, no stars, no planets, no us. The vacuum's restless ground state jitter is, in a very real sense, the reason anything in the universe has structure at all. We can actually observe the fingerprints of these primordial fluctuations. The cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space, carries an imprint of the density variations in the early universe. The Planck satellite and its predecessors have mapped this radiation with exquisite precision, measuring the tiny temperature variations across the sky. Those variations match the predictions of inflationary theory with remarkable accuracy. The statistical pattern of hot and cold spots, their relative sizes, their correlations at different angular scales, All of it agrees with what you'd expect if the fluctuations originated as quantum vacuum noise during inflation. This is one of the most extraordinary results in all of cosmology. The largest structures in the observable universe, structures spanning hundreds of millions of light-years, began as quantum fluctuations in the vacuum during the first sliver of a second after the Big Bang. The smallest scale in physics, quantum field theory at the subatomic level, is directly connected to the largest scale, the cosmic web stretching across the observable universe. And the connection runs through the vacuum. Now let's turn to something closer to the particle physics side. Because the vacuum doesn't just shape the cosmos, it determines the fundamental properties of matter itself. And the most dramatic example of this is the Higgs field. Every quantum field we've discussed so far, the electron field, the electromagnetic field, the quark fields, exists in a ground state where the field's average value is 0. The field fluctuates around 0, but 0 is the center. The Higgs field is different. Its ground state is not at 0. The Higgs field has settled into a state where its value everywhere in the universe is not 0, but a specific non-zero number. The vacuum of the Higgs field is displaced. The field is always on, always present, always at this non-zero value, at every point in the universe. This is called spontaneous symmetry breaking, and it has profound consequences for the particles that fill our universe. When particles like electrons and quarks move through the non-zero Higgs field, they interact with it constantly. That interaction gives them mass. Without the Higgs field's non-zero vacuum value, electrons would be massless, quarks would be massless. The W and Z bosons, the particles that carry the weak nuclear force, would be massless. The entire structure of matter as we know it depends on the fact that the Higgs field has this unusual vacuum state. Think about what this means. The mass of every particle in the universe is not an intrinsic, built-in property of the particle itself. It's a consequence of the vacuum state of the Higgs field. It's a property of empty space. Change the Higgs field's vacuum value, and you change the masses of all the fundamental particles. Make it 0, and electrons lose their mass, atoms can't form, chemistry doesn't work, and the universe contains no stable matter. The vacuum state of a single quantum field determines whether atoms can exist, whether stars can burn, whether planets can form, whether life is possible. The vacuum is not a passive backdrop. It's the stage and the script simultaneously. The existence of the Higgs field was confirmed in 2012 at CERN, when the Large Hadron Collider detected the Higgs boson, the particle excitation of the Higgs field, at an energy of about 125 giga-electron volts. Peter Higgs, François Englert, and Robert Brew had predicted the field's existence back in 1964, nearly half a century before its experimental confirmation. The discovery was a triumph, awarded the Nobel Prize in 2013, and it confirmed that the vacuum state of a quantum field gives mass to the fundamental particles. But the Higgs field also raises unsettling questions. The non-zero vacuum value of the Higgs field represents an enormous amount of energy filling all of space. This energy contributes to the vacuum energy density, the very quantity that is so catastrophically wrong when we compare quantum field theory predictions with cosmological observations. The Higgs field's contribution to the vacuum energy is large, far larger than the observed dark energy density. Why doesn't this energy dominate the expansion of the universe? Why is the actual cosmological constant so small compared to what the Higgs field alone would predict? These questions remain unanswered. There's another unsettling feature. Current measurements of the Higgs boson's mass and the top quark's mass suggest that the Higgs field's current vacuum state might not be the true, absolute lowest energy state. It might be a local minimum, a valley in the energy landscape, but not the deepest valley. There might be an even lower energy state somewhere else in the landscape. If so, The universe's vacuum is metastable. It's stable for now, potentially stable for billions of years more, but in principle, vulnerable to a transition to the deeper, true vacuum state. The mechanism for such a transition is the same quantum tunneling we encountered earlier when discussing the Schwinger effect. In that case, an intense electric field thinned the energy barrier, separating the vacuum from a particle-containing state, allowing the vacuum to tunnel through into a state with real electron-positron pairs. Vacuum decay works by the same principle, but applied to the Higgs field itself. The barrier separating our current vacuum valley from the deeper valley is finite. Quantum mechanics allows the Higgs field, at some random point in space, to tunnel through that barrier and settle into the lower energy state. This would nucleate a microscopic bubble of true vacuum, unimaginably small at first, smaller than a proton, but containing within it a fundamentally different version of physics. Sidney Coleman and Frank Deluchar worked out the detailed mathematics of this process in 1980, showing that the bubble, once formed, would expand outward at the speed of light, driven by the energy difference between the two vacuum states. The same quantum tunneling that can create particles from the vacuum can, in this scenario, destroy the vacuum itself. If such a transition ever occurred, the consequences would be catastrophic beyond imagination. The bubble of true vacuum would expand outward at the speed of light. Inside the bubble, the Higgs field would have a different value. The masses of all particles would change. The forces between them would change. Atoms would no longer hold together. Chemistry would cease to function. Any matter the bubble encountered would be instantly restructured according to the new vacuum's rules. The bubble would sweep across the cosmos, rewriting the laws of physics as it went, and nothing inside it would survive in any recognizable form. This scenario, called vacuum decay, is not science fiction. It's a genuine possibility within the standard model of particle physics, given current measurements. The probability of it happening is thought to be extraordinarily small, so small that the expected time for such a transition is far longer than the current age of the universe. We are almost certainly safe. But the very possibility illustrates how deeply the properties of the vacuum determine the nature of reality. The vacuum state we inhabit isn't just a background, it's a specific physical configuration. And different configurations would produce entirely different universes with entirely different physics. This connects to a broader point about how the vacuum shapes reality. In quantum field theory, the vacuum state determines which particles exist and how they interact. The vacuum isn't just the absence of particles, it's the stage on which the entire drama of particle physics plays out. And the properties of that stage, which fields have non-zero vacuum values, which symmetries are broken, which particles acquire mass and which remain massless, these properties determine everything about the physical world we observe. If the Higgs vacuum value were different, electron masses would be different, atomic structure would be different, the periodic table would be different, chemistry would be different, biology would be different, or impossible. If the vacuum state of the strong force fields were different, protons and neutrons might not form. Without protons and neutrons, there are no atomic nuclei. Without nuclei, there are no atoms. Without atoms, there is no matter in any recognizable sense. The universe we inhabit, with its specific particles, specific forces, specific constants, specific chemistry, and specific capacity to support complex structures and life, is a consequence of the specific vacuum state the quantum fields have settled into. Other vacuum states would give other universes, most of them probably sterile, empty of the kind of complex structure we take for granted. We live in a universe whose vacuum happens to support complexity. Whether that's a coincidence, a selection effect, or a consequence of deeper principles we haven't discovered, is one of the great open questions in physics. Let's step back now and consider the full picture. We began this journey with a seemingly simple question. How can empty space produce particles if there's supposedly nothing there? And the answer, laid out across everything we've explored, is that the premise of the question is wrong. There is not nothing there. So-called empty space is the ground state of quantum fields that fill every point in the universe. Those fields have energy. They fluctuate. They respond to external conditions. They determine the properties of matter and the structure of the cosmos. The vacuum is not the absence of physics. It is where physics lives. Particle creation from the vacuum is not something from nothing. It is a field process. The fields are already present everywhere. The potential for excitation exists at every point. Under extreme conditions, when sufficient energy is provided by an intense field, a violent acceleration, or the warped geometry of space-time near a black hole, those quiet ground-state fluctuations are driven past the threshold into real, detectable particle excitations. The energy always comes from somewhere. The conservation laws are always respected. What changes is the state of the fields, from ground state to excited state, from vacuum to particles. This understanding didn't come easily. It required centuries of physics, from Faraday's intuition about fields filling empty space, through Maxwell's equations, through the quantum revolution of the early 20th century, through the development of quantum field theory, through the theoretical breakthroughs of Schwinger, Unruh, and Hawking. Each step built on the last. Each step revealed that the vacuum was richer, more complex, and more physically active than anyone had previously imagined. And the story is far from over. The vacuum catastrophe remains unsolved. The nature of dark energy remains mysterious. The question of whether the Higgs vacuum is truly stable remains open. The quest for a theory of quantum gravity, which would unify our understanding of quantum fields with Einstein's curved spacetime, continues. These are not minor loose ends. They are among the most profound unanswered questions in all of science. And every single one of them involves the vacuum. Every single one requires understanding what empty space really is and how it behaves. The vacuum is the foundation on which the rest of physics is built. Particles are excitations of it. Forces are transmitted through it. The large-scale structure of the universe grew from fluctuations within it. The masses of fundamental particles are determined by its state. The fate of the cosmos, whether it continues expanding forever, accelerating into cold emptiness, or undergoes a catastrophic phase transition that rewrites the laws of physics, depends on its properties. When physicists study the vacuum, they're not studying nothing. They're studying the most fundamental layer of physical reality, the substrate from which everything else emerges, the ground floor of the universe. And the fact that this ground floor is not empty, that it's a rich, dynamic, physically active state capable of producing matter under the right conditions, is one of the most important discoveries in the history of human understanding. The next time someone tells you that space is empty, that the vacuum is nothing, that there's nothing between the stars or between the atoms in your body, you'll know better. The vacuum is full of fields, full of energy, full of potential. It shaped the cosmos. It gives particles their mass. It drives the accelerating expansion of the universe. And, under the right conditions, it produces matter from what looks like thin air, but is really the richest and most fundamental state of nature we know. Empty space is not empty. It never was. And understanding why that's true is one of the deepest insights physics has ever achieved.